So, so the last thing we're going to talk about in the inelastic cases is when we have non-ideal column behavior. So oftentimes columns don't act like in the perfect Euler case, and they might fail at lower loads. And the main reasons for this are eccentricity, which is defined as when the load does not go through the central axis, and then the other two reasons are imperfections and residual stresses, which are due to manufacturing and assembly errors. All right. So to account for this, we can use something called the parabolic equation or the parabolic method. So we can plug in the yield strength over 2 for the critical stress, all right, in the Euler equation. So the critical stress, we're going to plug in sigma y over 2, and we're going to solve for this critical ratio of KL over RG, right? So if we just rearrange this equation, and we bring this down to the bottom, what we end up getting is that our KL over RG is going to be equal to the square root of 2 pi squared over times E over the yield strength, right? Right? So what we can then do is we can plug in this critical slenderness ratio times the K factor, and we can plug it in to our original equation for the critical stress, and we can solve for the the critical stress for various KL over RG terms, right? So if you had the extreme case where KL over RG would be 0, so that would be the shortest column that could be possibly imagined, sigma critical would equal to sigma y, or the yield strength, and then at KL over RG is equal to KL over RG critical, sigma crit will be equal to the yield strength over 2. So in between these two extreme values, we get a parabolic line that I'm drawing over here, right? All right. So on the KL over, so when KL over RG is less than or equal to the KL over RG critical length, we can use the parabolic equation to account for, determine whether or not something will fail. And then if KL over RG is greater than KL over RG critical, we have to use the Euler method, right? And this is all to take into account for imperfections in columns. So if we have the idealized case where Euler would go all the way to the yield strength of the material, what's been experimentally found is that there are these failure points that occur along the line. So by doing that, those failure points would occur outside this parabolic region. So the parabolic region is much better at predicting the actual behavior of the columns.